Now we'll calculate here the strain energy in the case of impact load, and based on the formula that we are using a strain energy, we can calculate what is the maximum possible stress is developed. So impact loads refers to the sudden application of a force on a structure, typically resulting in a high stress condition that can lead to the deformation, fracture or failure. Suppose the part is not designed in the case of impact load and will design only for static load. In that case, the chance is that the stress will exceed than the fracture strength and or the yield strength, and there is a permanent deformation or maybe a failure. Up till now we have done the axial load in which the force is applied through the longitudinal axis. Because of this, the axial loads can have either compression or tension in the material. So when the impact load is applied axially, the effect of the structure will depend on the magnitude, duration and the direction of the force. And if the force is large enough, it causes the material to yield or deform or fracture. For example, consider here a heavy object of mass equal to m is fall through height is equal to h. So through this height, when the body will fall, it will going to make the impact, and entire kinetic energy is used to convert into the work under the ideal condition, and that work is stored in the bar, and we can calculate here the strain energy stored due to the work done or change in kinetic energy or change in potential energy of the object. In this situation, the bar can generate a large axial load that can cause the column to buckle or bend, and there is a failure. To prevent such failures, we must consider the impact load that a structure may be subjected to and design it accordingly. Take another example here. We have a vertical bar at the bottom of which we have a collar is fitted, and in this case the movable load W is fall through height equal to h. So when the movable load will strike to the collar, so there is a conversion of the potential energy into the work done. So we can apply the law of conservation of energy here, that is the change in kinetic energy plus change in potential energy equal to work done, and this work done is stored in the form of strain energy. So once you calculate the strain energy due to the impact load, then you can find out here what is the stress developed in the material. Naturally, that stress developed will be more than the static load, that is the load is kept at the collar. Then the stress developed will be called as static stress, and correspondingly we have static deformation. The strain energy stored within the material during the impact load can be significant, and it can result in a permanent deformation or even a fracture of the material. In many cases, the strain energy stored within the material is dissipated as a heat, sound or other forms of energy during the deformation process. But for our discussion, we'll consider here that entire potential energy is converted into work done. We assume that no energy is lost in the heat or sound or any other form other than the work done. So only the conversion of kinetic energy and the potential energy into the work done we'll consider. So in this case, we can apply the work energy principle and we'll neglect the energy dissipated in the form of heat and sound. So according to the work energy principle, we have change in kinetic energy plus we have change in potential energy must equal to the work done, and this work done is same as our strain energy equal to U. Out of that, kinetic energy change is given as 1 by 2 into mass m into final velocity square minus initial velocity square, plus we have change in potential energy equal mgz2, initial potential energy is mgz1, is equal to the strain energy. Now this equation is a physics equation, so you have to prefer here SI unit. Mass you have to take in kg, velocity you have to take in meter per second, then U will be in joules. So prefer for this equation the SI units rather than the conventional machine design units. To develop the expression for strain energy stored in a body when the load is applied with impact, we'll consider here one bar of uniform cross section of length equal to L, and the top end is fixed. Bottom end we have a collar, and in this case we apply here the load W, and this load is increased gradually from 0 to W. Because of this static load which is applied at the base, that is the deformation is equal to dl, and this load is increased gradually and is a stationary load. So this one is representing the static loading condition. Since here the load is not moving, it's a stationary load, so corresponding stress produced will be static stress, and the corresponding deformation dl is called as static deformation. So this value of dl will call it as static. Sigma static is same as equal to W divided by area A. So this one is the static stress produced due to the application of W on the area A, and we have static deformation will be same as the load multiplied by length L and divided by area divided by young modulus E. But we are not interested in the static loading, rather we are interested in the impact loading. So what we'll do here, we'll drop this load through a certain height and let we have a impact takes place on the collar. And then we'll calculate here what is the stress produced. That will be called as the impact stress. Naturally here, because of the impact here, the deformation will be higher value. That will be called as the deformation due to impact. Now consider the case here in which we have a load here is attached by certain means at a distance equal to h from the rigid collar, and this load is a movable load, and this load if dropped through the height equal to h, then the entire potential energy is get converted into the work done, and that is stored in the form of strain energy. Because of this, there is an instantaneous extension will take place that we called as a DL impact, and the corresponding stress produced will be called as here the impact stress. And we are interested to know what is the value of impact stress and what is the value of DL impact. This one is initial situation, and second one is representing here the final situation. So before impact, the load is at a height equal to h plus DL impact, and after the impact it will attain a datum. So we'll set our this horizontal line as a datum. Initial condition will defined as 1 and the final condition will defined as 2. In this case, the initial condition we have total height is equal to h plus DL impact. So we have Z1, that is a potential head, will be equal to h plus we have DL impact. Since it is drop here, so initial velocity v1 will be equal to 0. Finally, we have z2, and since we have set up our datum here, we have value of z2 equal to 0, and after impact it will attain the velocity v2 equal to 0. At this stage we can apply the work energy principle and will neglect any energy dissipated in the form of heat or sound. In that case, we have change in kinetic energy plus change in potential energy is equal to the work done. So let me write this as work done WD is same as equal to the strain energy U. Change in kinetic energy here is 0. Change in potential energy is given as mg, which is same as equal to W, that is the weight of the load, which is a movable load. We have Z1 minus Z2, that much amount of work is stored. So we have W into Z1 minus Z2 is same as equal to the strain energy equal to U. So we have W. Here Z1 is same as equal to H plus we have deformation due to impact loading is same as equal to the strain energy, and this value of strain energy in the form of impact stress is given as 1 by 2. Corresponding stress produced will be called as impact stress. We have square of it multiplied by volume. Volume is same as A multiplied by L and is divided by the young modulus equal to E. So if we are able to solve this equation, then we can find out the value of impact stress. Once we know the value of impact stress, then we can calculate here the DL impact. We assume here the extension takes place within the elastic limit, then we have deformation due to impact can be calculated as stress due to impact divided by young modulus E, which is nothing but strain, multiplied by the original length of the rod, that equal to L. So these two equations you have to use, and you have to solve this equation for impact stress. Whereas the sigma static is W by A and DL static is WL by A. Naturally here, as you can see from this figure also, the deformation in the static condition is less as compared to the deformation due to impact. Naturally, we have more value of deformation in impact. Hence, corresponding stress of impact will be always higher as compared to the static stress. So once you apply here the work energy principle, you will get the change in potential energy that equal to W, that is the load. Total height change will be equal to H plus DL impact is same as equal to the strain energy, which is equal to 1 by 2 impact stress square divided by E multiplied by volume, which is area multiplied by length. And this value of the deformation due to impact loading can be replaced as impact stress multiplied by L divided by Young modulus. In addition to this, already we have defined the static stress is given as W by A and the static deformation is given as WL by AE. So we'll replace here the deformation due to impact from equation. In that case, we get W, that is the load W, is equal to H plus we have sigma impact, that is the impact stress multiplied by length L divided by Young modulus E is equal to 1 by 2 multiplied by impact stress square divided by Young modulus E multiplied by volume, which is A into L. We are interested here to know the value of impact stress. So what we'll do here, we'll multiply 2 times of E and divide by AL on the left hand side, and we'll make here a quadratic equation. So multiply this equation throughout by 2 times of E by AL. If you multiply 2 times of E by AL, on the right hand side we are left here with the impact stress. So we have impact stress square. And this term will shift to the right, so will become negative. It has to be multiplied by 2 times of E divided by A divided by L, and we have to write here W into H plus we have W into sigma impact multiplied by length L and divided by Young modulus E, and the sum must equal to 0. Let's expand this and try to write it the equation in a standard form. So we have impact stress square. Second term I will write as this term, which is equal to minus 2 times of E divided by A into L is multiplied by W into impact stress multiplied by length L divided by Young modulus E. Second term will be minus 2 times of E divided by AL multiplied by W multiplied by H. On the right hand side we have equal to 0. So as far as the second term is considered, the Young modulus term will be get cancelled, length will be also get cancelled. So we have impact stress square minus 2 times of W by A will club in a bracket. So we have 2 times of W divided by A multiplied by impact stress minus, here also we can club 2 times of W divided by A in one bracket. What is left is H into E divided by L, and the right hand side equal to 0. So it's almost a quadratic equation here. So we'll write this equation in standard form. We have A into X square, where X is same as sigma impact, plus we have B into X, where B is equal to minus 2 times of W divided by A, plus we have constant C. So whole this term is a constant C must equal to 0. So if you compare this equation, the coefficient of sigma impact will be equal to 1. So we have value of A is equal to 1. This entire term is equal to B. So we have B is equal to minus 2 times of W divided by A. And this last term here is C, which is equal to minus 2 times of W H into E divided by AL. And the roots of the quadratic equations are given as x1, x2 is equal to minus B plus minus under root of B square minus 4AC upon 2 times of A. Now as far as the W by A is considered, we can replace W by A is equal to sigma static. So let's replace here the W by A is equal to sigma static. We'll get here minus of 2 times of sigma static. And the C we can change similarly. W by A we can replace as sigma static. So we have minus 2 times of static stress multiplied by H multiplied by E divided by L. So we'll substitute this value here and we'll solve for sigma impact. The remaining part of the derivation we will discuss in the next video, that is in part 2. The video you are watching is from the app, which is the Mohod class app available on Google Store. And in this app, we'll cover all subjects involved in mechanical engineering for GATE. Join the course directly from your mobile. The link is given here.